Hey everyone, welcome back to Engineer with Musa. This is Mohammed, and we're going to go over another example problem in episode 3 of Engineer with Musa, and we're going to still be talking about statics problem. So now this episode is very special because this particular engineering problem is a problem that I came across on an interview question, and I want to share it with you all so you guys can better prepare yourself for interviews in your classroom and your static engineering courses down the line. So this was the problem. So we have an interview problem here. And I'm going to go ahead and paste it. So they said to me on an interview, draw us a beam with a fixed support, very important, fixed support, and essentially find the V&M diagram, shear and moment diagram for this. And I said, okay, here's how I'm going to solve it. And actually the way I solved it was correct, and the interviewer was quite impressed. So now let's go ahead and walk you through it. Now I'm going to go ahead and do all of my calculations in green so that you can see what's going on. So here we had our beam, and first thing first, we have to draw our free body diagram. So our FBD kind of looked like that. We had our distributed load of omega, cool. And so this is our beam. And then we had a normal force. We had a shear force. And we had a moment. So this is NA, normal force A, VA, shear force A, and moment at point A. So this is going to be point A, and this is going to be point B. And same thing goes for the other side. We're going to use positive sign convention. So we're going to have on this side VB. We're going to have our normal NB, and we're going to have our moment MB. And so we have our omega, and the length of it is length L, the entire span. So now first thing we need to do is find the sum of the moment about point A. So again, go ahead and write the sum of the moment about point A with the positive sign convention being counterclockwise, always. And we go ahead and solve. So we go ahead and say that the distributed load over here, omega, about point A is going to be equal to minus omega times L over 2. Because we want to take our distributed load, multiply it by the entire length of the beam, so we get a point load, and then the moment is going to be about point A at the center. So that's how I came up with the M times L, which is the entire loading, and then it's going to be acting at the center, so at L over 2. So hopefully that made sense. And then the next portion is going to be actually the shear at point B. So we're going to be looking at this guy over here. That one times the length of L, that's going to give us the moment. And then we're going to have the moment at point B. So we got to take into account that one. And that one is a positive sign convention. And lastly, we're going to have the minus MA right over here. Okay, and that one is in a negative sign. So I believe actually this value over here is supposed to be a negative as well, because it is, acting counterclockwise. It's acting clockwise, my apology. Clockwise is the negative. That's why I put a negative over here. So now once we solve for this, we will indeed have minus omega times L squared over 2 minus VB times L plus MB minus MA equals to 0. And then we can kind of sort and simplify something. Awesome. Now we can look at the sum of the forces in the y direction. And that will give us, let me zoom out a bit so we can get the whole picture. Sum of the forces in the y direction giving us that positive sign convention being up equals to 0. And so we notice that we have vertical forces VA, and we have VB, and we have omega. So these are 3 targets. So we notice that VA minus VB minus omega times L is equal to 0. Cool. So we know that VA minus VB is equal to omega times L. Awesome. Awesome. So we need to note here that VA and VB will be equal to each other due to the fact that the loading is symmetric over here. So we know that omega is a loading that is across the entire beam, and we can analyze and make the correct assumption that the loading at this side in the vertical direction will have to equal to the loading at this side in the vertical direction in order to support this entire omega load. So with that assumption, and of course we have to write down our assumptions, we can say that due to symmetry, VA is equal to VB. Okay, so now that's going to leave us with VA is equal to VB, and we know that VA is going to have to equal to half of omega L. And that goes for VB as well. So therefore, it's equal to omega L over 2. Now, that's awesome. And now we have to go back into this sum of the moment equation that we looked at and say minus omega L squared over 2 minus omega L over 2, and this is equal to that because of this. Hope that makes sense. Then times L plus MB minus MA is equal to 0. So now let me just move this down a bit. And then we have minus omega L squared over 2 minus omega L squared, omega L squared over 2 plus MB minus MA is equal to 0. And we can make the same assumption in terms of the moment and say that MB is going to have to equal to MA. It's just going to be an equal and opposite direction. So due to symmetry, MB equal to MA. Again, if you look at here, the moment is going to have to carry the same amount of moment due to the symmetric loading. So now we go back to the calculation and say MB is equal to minus omega L squared over 4, and that's going to be the same case for MA. So now we can go and draw our 3D body diagram. Excuse me, not 3D body diagram. We can draw our shear moment diagram. And that will look something like this. Let me actually move all of this out of the way. And then resize this. Okay, so for our V diagram, we have VA, like I said down here, it's going to equal to omega L squared over 2. So I'll go ahead and write that over here. Omega L over 2. And then we know that it's going to be intersecting this axis over here and then coming down. And so that is going to look something like this. And this is going to be the positive side, and that's going to be the negative side. It will jump up, follow this line across, down to the minus omega L over 2, and then it will jump back up. So it will follow this path. I like to draw arrows in order to make sure I know how my moment and shear are flowing across the beam. So now we jump to our moment. And so we have our moment on the left hand side equaling, what was it? It was minus omega L squared over 4. So we jump over here, minus omega L squared over 4. And then we know that down on the other side it's going to be also minus omega L squared over 4. And so the path it's going to take is something like this, something like a parabola. And I'll explain to you in a second why. And so we know that down here is negative, negative, and that's positive. So here we have all of the area being positive, so that means that it will need to have a positive slope all the way until it gets to the center. Once it reaches the center, then the values in here start to get negative. That's why we have a negative slope over here. And then it jumps back up to 0 because it always needs to end at 0. So it goes down, cross, down, and then up. So that is your shear and moment diagram. Hope this makes sense. If you have any questions, please leave it in the comments and enjoy.